Alright, hello everybody, this is Dr. Pennington again. In this video I'm going to be talking to you about a concept that seems rather odd, a little weird. It's about something called hybridization. Now, you guys have heard the term hybrid before, you know, in terms of flowers or when you breed dogs or whatever. Hybrid is when you take two things and get out something else. It's kind of like if you breed a bulldog and a shih tzu, just imagine what you get out. We're going to talk about that in class. Anyway, the point that I want to make here is atomic orbitals, those on carbon or hydrogen or whatever atoms you might be talking about, will do something in particular when other atoms come close to them. The fact is that the structure of carbon, this is the Lewis structure of carbon, but you guys know that structure is actually tetrahedral. So you know the actual structure of methane here is something like that. Alright, the tetrahedral shape. Now for ethene here, where we've got electrons going in three directions around each carbon, then that actually means each carbon is trigonal planar, so we have a 120-degree bond angle, so the actual Lewis structure looks like this. And then when we get to ethyne here, or acetylene, we have electrons going in two directions, so the groups around carbon should be 180 degrees apart, and in fact they already are. So valid Lewis structure here, valid structure here, and valid structure here as well. But we've got to talk about in this video exactly why this is the case. When we look at carbon, for example, in methane, if we just look at the electron configuration of carbon, it's 1s2, 2s2, 2p2. 6 electrons, 4 of which are valence electrons. Those are the 4 valence electrons in carbon. All right. Now, if we just look at these on an energy scale, the fact is that the 2p orbitals are slightly higher in energy than the 2s orbitals. We also know the 2p orbitals are degenerate and that they're all the same energy. And we know that electron configuration looks something like this. Now, notice how many orbitals we have here, and these are atomic orbitals. Atomic orbitals because they're on an atom of carbon. Alright. In other words, carbon that's not come into contact with any other elements yet. Notice there is 4 atomic orbitals here. 1, 2, 3, 4. It doesn't matter whether there's an electron or how many electrons are in each orbital. The fact is there's 4 of them. 3 2p orbitals, 1 2s orbital, giving a total of 4 atomic orbitals. Now you'll notice these 4 orbitals are not all the same. But these 4 valence electrons are what carbon uses to make its 4 bonds. So if these electrons in these orbitals, if all the orbitals aren't the same, how is it that somehow the bonds in carbon are all equidistant from each other? Well, it's to do with the orbitals that carbon uses to bond to hydrogen. But we just saw on the last page that the orbitals on carbon are not all the same. So how can that account for the structure? Well, it's a particular process that carbon undergoes. And exactly why carbon does it? Carbon just seems to know when it comes across another atom. Emma, piss off, will you? Sorry, that's my cat. Okay. So there is something that's happening between these atomic orbitals, and they're doing something to come out with something else that allows for these 4 bonds to be equidistant from each other. More than likely what it's somehow given us are 4 orbitals that are all the same. And that's exactly what is happening. These atomic orbitals undergo a process called hybridization, just represented by the letter H here. And this hybridization occurs when the carbon comes into contact with hydrogen that, for example, it wants to form bonds with. We have 4 atomic orbitals. They all mix, and we get out 4 so-called hybrid orbitals. that, now notice I've drawn them this way, they're all degenerate, they're all of the same energy, and they all also have one electron. So if we go back to our carbon, each of these hybrid orbitals has a particular shape. It looks kind of like this. Alright, with a big bit on one side and a little bit on the other. It's a combination of an s and a p orbital. Now we don't need to worry about exactly why the shape is the way it is, but one thing we should worry about is why these are called Sp3 hybrid orbitals. Well, it's simply because you've taken 3 p orbitals and 1 s orbital and mixed them together. Therefore, the result is going to be 75% p, 25% s, and hence the name Sp3. These orbitals, then they're arranged around the carbon atom, and they look, I can't draw them exactly right here, but imagine that these two correspond to the two in the plane of the board. We've got one coming out towards us and then one going away from us. And these are the orbitals that overlap with the s orbitals from hydrogen to give us our bonds. So hydrogen, 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 because hydrogen. Because really all a bond is just overlap of orbitals. That's all that is. That's exactly what a bond is. So because these orbitals are maximally apart from each other, 109.5 degrees apart, that's exactly what gives rise to the shape of methane. In fact, every carbon that's just got single bonds around it is more than likely going to be Sp3 hybridized. This is an important thing to understand, particularly for those of you going on to organic. This is particularly important. Now, so that's one situation. And the thing I should say is each one of these bonds, a single bond here, that single bond has a particular name. It's called a sigma bond. Alright. Now, we're going to move on to Sp2 hybrid orbitals. And this is where we're going to look at ethylene here. Notice the difference. Single bonds, we've got a double bond here. So we're going to take our electrons, we're going to take our valence electrons from carbon again in our 2s and our 2p atomic orbitals, and we're going to put our electrons there. We're going to go through hybridization process again when it comes into contact with hydrogen. Kind of depends on how much hydrogen it comes into contact with. And in this case, let me erase that. In this case, what happens is we get something that looks like this. We have a situation where only 3 of our orbitals mix up. Sp2, if we go back to Sp3, that means 3 p orbitals, 1 s orbital. So this must mean 2 p orbitals and 1 s orbital. So in effect, these are the ones that are mixing together, and this one is left all on its own. So it's still there. These are our 3 Sp2 hybrid orbitals. That's our hybridization process. So we have 3 of these Sp2 hybrid orbitals. And when you have 3 orbitals, what's the best way to have them separated? Well, it's all in one plane, have them 120 degrees apart. Something like so. Alright. Now, you guys know carbon likes to make 4 bonds. This is only making 3 right now because we've only looked at the 3 hybrid orbitals that we've made. The 2p orbital is still present on the carbon. Alright, so really, if I just erase these, because I'm going to show you what the orbitals actually look like here. So here's our carbon, and I'm going to show one of our Sp2 orbitals, another one here, and another one here. And we're going to do the same thing with our other carbon. When we're talking about the ethylene here, this is 2 carbons, and both are hybridized in exactly the same way. So we're going to have one here, those 2 will overlap, one here, and one here. These are essentially mirror images of each other. Now remember what I said about overlap of an orbital? Overlap of 2 orbitals, that means a bond. So we've got bond here, bond here, assuming we have hydrogen atoms here. The shaded bits are where we form bonds, assuming these are all hydrogens. Alright, so if we were to label these, that's an sp2 orbital, so is that one, so is this one, and each carbon's got 3 sp2 orbitals. But each carbon also has the 2p orbital that's left over, and I'm going to draw this one in a different color, simply so you can see the difference. The p orbital, if you imagine the sp2 hybrid orbitals, these are all trigonal planar. They're all in a triangular flat plane, and if you look at the molecule side on, those 2p orbitals would look essentially flat. The 2p orbital that's left on its own goes 90 degrees to that, so essentially it goes up and down. It puts this orbital maximally far apart from the 3 sp2 orbitals. And each of those carbons has this sp2 orbital on it, has this p orbital on it. And this doesn't really show it. The p orbitals are actually much more diffuse than that, and there is overlap between these two. So as we saw before, when we have a single bond, this is essentially end to end overlap of orbitals. That's what we have when we have a sigma bond. So all these guys here, end to end, end to end, end to end, end to end, and end to end, these are all sigma bonds. This guy though, what gives each carbon its 4th bond, this isn't end to end overlap, this is side to side overlap, and that's called a pi bond. So what that means is between the 2 carbons we have all these bonds to hydrogen, 2 on each case. We have a sigma bond between the 2 carbons, but then we have another bond between the 2 carbons, which is a pi bond. Overall 2 bonds here. These are 90 degrees to each other, like I said. The bond angle here is 90 degrees. That is sp2 hybridization. And then when we get to the last one here, if we're going to do our energy diagram once again, we have our 2s. Oops, crap. We have our 2p. Well, bollocks. I don't want to confuse anybody, so let me erase that crappy drawing again. 2p. Put in our electrons. Alright, bear in mind this is still carbon that we're talking about. We undergo the hybridization process, except in this case, sp, as you would imagine, just means 1 hydrogen and 1 p and 1 s orbital. So if we put in 2 atomic orbitals, how many hybrid orbitals should we get out? Well, as you would imagine, it's 2. 2 of those. But then that leaves 2 p orbitals left over. We still have a total of 4 hybrid orbitals, so we're going to put those electrons here. And so when we look at our carbon again, when we have 2 orbitals like this, what's the best way to spread them apart? Well, of course, the best way is to put them 180 degrees apart. One like that, and one like that. And then when we look at the other carbon, we've got exactly the same thing. Alright, and when these guys come into contact with hydrogens, we have 1 bond here on the end, like so. Now before we go any further, what sort of bonds are these again? Remember, these are end-to-end overlap of orbitals. These are sigma bonds, so-called single bonds. But each carbon wants to make 4 bonds. And we've used the sp hybrid orbitals here, so we've got to use these 2 as well. Now, once again, just imagine that the sigma bonds are all in one plane. So you're looking at the molecule, say, from top down. Each carbon still has 2 p orbitals, and these lie at 90 degrees to each other. So if one is pointing left and right, one is pointing out towards you. So if one is going up and down, say one's going to be coming out towards you, kind of like that. I can't really show it very well. But I'm going to show 1 p orbital going straight up and down, And this overlap here is going to give us rise of one bond. Except what sort of bond is that? It's a pi bond, like we said before. So here we have bonds going, the sigma bonds are going straight left and straight right. The pi bond here is going straight up and straight down. There is another pi bond here from each of the two p orbitals on each carbon, because notice we've only used one p orbital on each carbon so far. And that other p orbital is going to be hard to show, is going to be going away and coming out towards us. So if I show that, what I'm trying to show is, with my limited artistic ability, is this overlap here with these two coming out towards you and overlapping like so. So when we do that, what that really means is, when we look at our molecule, we have sigma bonds in each case, constituting to our single bonds. And then on each carbon we have two extra p orbitals, that's these two, that overlap with each other on the p orbitals on the other carbon, giving us a pi bond in each case. So one here and one 90 degrees to that, giving rise to two extra bonds between the carbons, or triple bond. So the book does go into some more hybridization, Sp3D and Sp3D2. For right now, I just want to have us focus on Sp3, Sp2, and Sp. So your atom is Sp3 hybridized when all it has is single bonds to it. Sp2 hybridized when it's got a double bond to it, and Sp hybridized when it's got usually a triple bond to it. Alright, so if we just look at one thing here, if I was to say, well, here's a molecule of hydrogen cyanide, and I was to ask you, what's the hybridization about each of these two atoms? We aren't concerned about the hydrogen. Well, what we've got to look for is how many directions are electrons going in around those atoms. If we go back to the first slide here, and we look at this carbon. So the question is, well, how many directions are electrons going in around that central atom? Well, of course, it's two directions. Around this carbon, it's also two directions, which means orbitals that are 180 degrees to each other, and the only possibility for that is Sp hybrid orbitals. And if one of the two atoms is Sp hybridized, the other one must be as well. Now, here's a simple way to remember which is which. All right, if you have two directions, your S's and your P's, the number of S's and P's that you have, must add up to 2. 1 S, 1 P equals 2, therefore two directions, Sp hybrid orbitals. Here we've got 1, 2, 3 directions, therefore we've got to have S's and P's adding up to 3, and we can only ever use 1 S at a time because there's only 1 S orbital. So if 2 directions means 1 S and 1 P, 3 directions must mean 1 S and 2 P, 4 directions must be 1 S and 3 P. Alright? So the total number of S's and P's here must add up to the number of directions around the central atom. So 4 always means tetrahedral. 3 always means trigonal planar. 2 always means linear. Alright? So Sp3 always means tetrahedral. Sp2 always means trigonal planar. And Sp always means linear. Alright? So when we go to here, the first thing that we should know, based on what I just said, is that each of these atoms has to have the same hybridization. And it's either going to be Sp2, Sp, or Sp3. So, let's look at the carbon. How many different directions are electrons going in around that carbon? Well, it's 1, 2. Therefore, 2 directions, the total of my S's and P's must be 2. Therefore, that's Sp hybridized. When we look at the nitrogen, electrons are going in 1, 2. Remember, we're counting the lone pairs as a direction here, as we have done before. 1, 2 directions must be Sp hybridized. Let's do another one. This is formaldehyde. Now let's draw the Lewis structure. put on those lone pairs. Alright. And I'd ask you here, what's the hybridization about each atom? We're never concerned with hydrogen here, it's just the non-hydrogen atoms. Carbon. How many directions are electrons going in? Well, that's 1, 2, and 3. We know that means trigonal planar, but an angle of 120 degrees. But 3 directions here must be in 1s and 2p, or sp2 hybridized. And if the carbon's sp2 hybridized, so must be the oxygen, but let's check. 1, 2, 3 directions. Well, dude, what do you know? Alright, one more. And I'm going to draw out the structure of ammonia. It's not a valid structure in terms of the 3-dimensional accuracy, but we can certainly have a go and figure this out. Ammonia. Nitrogen, electrons going in 4 directions. 4 directions must mean sp3 hybridized. 1, 2, 3, 4. Alright, and there we go. That is orbital hybridization. Thank you.